examine some of the examples that we had. Sorry that we had the break in the sequence, but I guess we're not losing, in terms of the number of workshops. We're still going to have the same amount. And today we're transitioning to a new topic, which is logistic regression. And most of you have had already 761, I guess 780, 781, and some of the advanced classes you probably covered, some aspects of it at least. But nonetheless, I see there's a sequence kind of logistic leading to the multi-level kind of problem. And then from the multi-level problem, if you have more than one DVs, to measurement models that basically deal with the same problem. Because what we have at hand is basically a dichotomy here in terms of the dependent variable or the outcome variable that we're looking at. So it could be present absent, or it could be agree disagree, or it could be any type of a dichotomous basically outcome that we have there. By the way, it doesn't have to be 0 and 1. It could be 100 and 101, or it could be A and B. The numerical assignment really doesn't really matter here. All we care about is that we have two categories in there. And then, so it could be wrong, right, or got it right, got it wrong, agree, disagree, was absent, present, these types of things. And the whole difficulty in terms of, predicting where you're going to be, and of course, you're going to have a number of predictors. Typically here, what we'll be covering is one predictor. So we're going to be looking one predictor at a time. As a matter of fact, the predictor that we use for the illustration is also a categorical variable, because I think that it makes sense to start with categorical variable. As a matter of fact, the dichotomy in terms of the IV and the DV is also a categorical variable. So the whole thing really becomes a contingency table problem that can be evaluated with a chi-square statistics in terms of the observed count and the specific, because if you think about it, you have the DV and it has two outcomes, and that could be like a vertical line or horizontal, doesn't really matter. And if this is horizontal, then the vertical line is going to be your IV, which is going to be also dichotomous. So you're going to have classification table, basically 2 by 2, what we call contingency table. And the whole problem can be solved pretty much with a chi-square statistic in terms of the significance. Can I predict the group membership with respect to what I already know in terms of the DV that I'm trying to estimate here? So it's really a classification procedure, but there is an idea of a threshold here, and the thresholds are going to be more important as we transition to the multi-level problems. Because basically there is going to be a level of difficulty or a level of knowledge, or maybe a level of attitude or aptitude or whatever it is that we're measuring, that we'll have to calibrate and determine how big it is for you to be classified in this category as opposed to the baseline category, if you choose the baseline category to be really the ground category, so to speak. It doesn't really matter, because sometimes we solve this type of a problem also in descending order, so we can choose that to be a reference category, and that to be, kind of the category that we're predicting. And the extension of this type of a thing is, of course, a multi-level problem, which could be actually treated as what we call nested dichotomies. So, for example, if we're looking at Likert scale and evaluating which category are you going to be attracted to, you can treat that as basically one logistic problem here, then another one here, and then another one here. So we call it's a nested dichotomy kind of thing. Now there are some other approaches. One of them is based on the idea of cumulative thresholds. And when we talk about the multi-level examples, specifically we're going to be talking about the proportional odds model, which basically calibrates these thresholds and that the betas, stay the same regardless of which category you're going to be predicted to. So this is type of an arrangement where you have something that increases, in intensity or increases in agreement. So the Likert scale would be a perfect example of that, but it doesn't have to be Likert scale. It could be just a 3 thing, not good, okay, kind of excellent. And if you have 3 levels, of the DB that we were trying to predict how many thresholds we're going to have. If you have 3 categories, there's going to be 2 thresholds, yeah, because we need a threshold from going no good to okay, and then you need another, you know, from going to okay to excellent, yeah. So the number of thresholds that you have to estimate is n minus 1, n being the number of categories, or k if you choose k. K is a more popular, you know, designation. Very severe, or no distress, mild distress, moderate, kind of very severe, and significant distress here. So how many thresholds do we need here? Okay, 4 thresholds because we have 5 categories, 5 minus 1 is going to give you the more important idea is that the thresholds are not necessarily going to be even. Okay, so the whole idea of assigning numbers 0, 1, 2, 3, 4, and 5 is kind of an arbitrary assignment. In other words, when we assign these types of numerical expressions here to each step, because we can think about it as conquering the steps, okay, as you climb up the ladder or the Likert scale, okay, the distance, of course, here, even though numerically it could be 0, 1, 2, 3, 4 kind of thing, of course, it's not going to be the same threshold. And we'll see it with the examples when we get to the multi-level, you know, kind of problems. So moving forward, okay, I probably already showed this slide before, but this is the ordinal mobility scale, where we can see that assignment of the particular numbers to these specific categories is really arbitrary. And we, of course, we have kind of a ceiling and a floor effect too. In other words, we know that the situation could be worse than laying in bed, because I might be laying in bed and I can still use the bathroom or something like that. You know, or I could be totally paralyzed, meaning it's even worse than that, but I don't have any number to express it, kind of thing. Yeah. And on the other side, okay, maybe aided walking and unaided, there's all kinds of different walking, okay? I still might need some support, or I can walk only, 10 steps. Or it could be a situation where I can run like Usain Bolt or something like that. Okay, so there's not really a limit here. And as a matter of fact, when Mike Lineker was working with rehabilitation centers in Chicago, and they were using this type of a scale to assess how patients are improving. Okay, one of the problems was that the patients were still improving, but there was just simply no category that could be, expressed here. In other words, they were always getting 4, and people in some cases, you're always getting 4. Okay, you stopped improving, which was not the case. They were still improving, but they were simply walking, but they're improving still, and they're walking. And the same kind of thing was happening on the other side. And of course, when they were using this type of a scale, they were using that with a number of items that the clinicians were evaluating with respect to how the patients are recovering from car accidents and things of that nature, or from severe injuries and surgeries. And they were looking at a number of items at the same time. And that's where the measurement model comes in, like a Roth model. But of course, we can tackle this type of a problem also with a multi-level regression. In other words, you don't want to do just an order regression here, okay, to predict your mobility. Let's say if you had the number of hours that you spend with a patient, or the number of rehabilitation sessions or something like that, and predict how well you improve, we realize that the thresholds here between the respective categories are going to be different. In other words, transition maybe from the wheelchair to unaided is a huge transition, okay, maybe. But the transition from unaided to walking, maybe it's a smaller transition than from here to here or here to here. And not to mention that the whole thing in terms of the assignment of the numbers, well, why not use a 10 scale, like this, which becomes actually a little bit even more confusing, because at least here I know that 2, okay, I have to observe the patient in a wheelchair, but if I don't define certain categories, and I say wheelchair, what does it mean to be 4 in wheelchair as opposed to 5? Is that electric wheelchair as opposed to, I can roll with it? And these types of things, unfortunately, we see it very common, and we subject people to these types of scales. And certain categories are not even clearly modified, and it's just a guessing game what it is, wheelchair 4, or what is it here in terms of 3 even, And everybody going to interpret these numbers, a little bit different. And these types of a situation is for example, when you report to emergency room and they ask you on a scale from 0 to 10 how much distress or pain you're in. Well, if I'm just a toddler or maybe a young kid and I have never experienced really pain and I have my first false tooth, I'm going to be like, oh my God, yeah, and I'm going to be saying 10 or 9 or something like that, okay? On the other hand, if you have maybe a middle-aged patient that went through cancer treatment or something like that, okay, the same distress that they're experiencing physically, they will be reporting in much lower. So, you know, it starts all with the definition, proper definition of the categories. And then, of course, I can even exaggerate, and nobody can say, okay, that this is going to be way worse than necessarily this. So these are the types of problems that we're encountering when we're dealing with ordinal kind of progressions. You know, the best that we can do actually is to apply the multi-level regression and at least calibrate the thresholds. But it's all tied in, of course, with how we define, you know, the functioning of the categories. So some concepts, and again, I emphasize them a little bit more probably, but like everything that we're saying in regular regressions, because the general linear model regression was 1 unit increase is associated with so much increase, and that was your, on the dependent variable, and that was your beta coefficient basically. Yeah? So if the beta was 0.5, 1 unit increase on X was associated with only half of a gain in terms of the dV. Now the situation here is going to be a little bit different because the beta is actually a ln of ratio of odds. And ln of a ratio of odds is actually a loaded unit. So we have to work in terms of the dV now with loaded units, okay? Because ln of odds is loaded. And we pretty much interpret loaded units like z-scores, okay? So if the loaded unit is -3, it means like really a -3 in terms of z-scores in terms of penalty. If it is, you know, +3, it means, you know, way better, you know, outcome expected, you know, as a matter of fact, better than 90% of that or 99% of the cases. Yeah. So typically, since we know that whatever is reported in beta represents a loaded unit movement in terms of the dV, it's convenient to actually exponentiate the beta coefficient. So if I have a ln of something and I exponentiate it, then I get rid of that ln, yeah? And then what I'm left with is really a ratio of odds, okay? And it's much easier to interpret the ratio of odds as opposed to, you know, just dealing with loaded. Now, and I've been trained to kind of interpret, you know, loaded units and the movements because in rush models and item response theories, we're dealing exclusively with loaded unit movements, you know, but if you're not trained in it in terms of, you know, interpreting, then it's easier. And as a matter of fact, with SPSS, when you run a logistic regression, it will give you the EXP of this ln of odds, which is really a loaded unit, and then you can directly interpret that as so much higher, so much lower, you know, odds. And then, of course, we're extending the same idea, and we're going to be dealing with cumulative thresholds when we move to the multi-level, you know, analysis. So now let's see how we translate in practice. So we start with a ratio, and let's say my success of being in a higher category, or my success of passing an item, or my success of being successful in my rehabilitation program, or endorsing of an item is 0.8. Okay, so it's like 80% of a chance. Yeah. So the failure rate is going to be 1. We know that the total probability has to be 1. Total probability is always 1, yeah? So the failure rate is going to be 1. Well, if the success is 0.8, okay, then the failure has to be, if these are complementary events, of course, we have to mention, it's going to be 0.2, yeah? Because it's either this or that, so there are complementary, there is no third outcome, yeah? Because in a logistic regression is a binary outcome always, yeah? Either presence, absence, agree, disagree, succeeded, you know, failed. So this is the kind of thing that we're looking at, and the ratio of these two things gives you 4, which is the odds of, let's say, passing an arithmetic item or something like that. Yeah. So if I give you a relatively easy arithmetic problem, and you're highly skilled in mathematical ability, you will be 4 times more likely to pass a particular item because the proportion is 0.8 to 0.2, yeah, which will give you the 4. So the 4 already represents the odds. Okay? And then when we take the ln of odds, it will give you something which is called the logit unit, which is actually what the beta, reported beta coefficient logistic regression is the ln of that, of these odds. Okay, so you have the odds, and then you take a ln of that. So this is like being 1.39 z-scores, you know, above the mean kind of thing. Where mean in this particular situation would be point of indifference. I can either pass or fail the item. Yeah. And how do you get back to odds? I said that we have to exponentiate, because the way to get rid of the ln, you take the exp of that. So these terms are going to cancel themselves out. And then you're going to be back to your odds, which is what we started with, you know, which is the 4. Yeah? And then how do you get back to the probability of fail? It's going to be 1 divided by 1 plus odds will give you the 0.2, which is the probability of fail. As a matter of fact, the probability of success would be 4, which is the odds, divided by 1 plus odds. So again, odds divided by 1 plus odds will give you the probability of success. Okay, or you can do 1 minus the failure rate, yeah? So it's 1 minus 1 divided by 1 plus 4 will give you the 0.8. So there's numerous ways of getting to the same answer, basically. But this is where we started with. We started with the probability here, and we worked through the simple math, and we basically get back to the probability statements, you know, again. So you think about, if my beta is 139, from a logistic regression, okay, that would mean that my probability of being in a lower category or in a fail category or absent, okay, is going to be what? 0.2, yeah? And my success rate or present success agreed, you know, answer the question correct is going to be 0.8. And the probabilities have to, of course, you know, complement themselves, you know. So this is how you would transition from that beta back to the specific probability, okay? And then what the system will do, okay, this probability is higher than this, therefore I'm gonna put you in a pass category, okay? So everybody that is associated with this particular beta, okay, they will be automatically classified in the success category. Of course, if you have a situation when there is a point of indifference, so you're as likely to pass as to fail, then the ratio of a pass to fail, well, it's got to be 0.5, yeah, is the pass. Well, the fail has to be 1 minus 0.5, which is 0.5, yeah? So the odds are going to be 1. In other words, you're indifferent, yeah? It could go either way, yeah? It could go either way. And then if I take a ln of 1, will give me 0, and that ln of odds is kind of like looking at the z-score, yeah? My z-score is 0, meaning I'm equally likely, yeah? I could either pass or fail, and I cannot use really a good job. So then when we exponentiate that 0, we're going to be back to odds, which is 1, which is the point of indifference. And then 1 plus the odds will give you the 0.5, which is the success rate, yeah? And, or I'm sorry, the failure rate. The success rate will be odds, which is also going to be 1, divided by 1 plus odds. So 1 over 2 is going to give you also 0.5, or 1 minus this failure rate will also give you the probability of fail. In other words, if you had this kind of a situation where the exp, I'm sorry, the beta would be 0 from that regression equation, the system will not be able to classify where you are, okay? Now, it will be very unlikely event that your beta will be exactly 0, yeah? Because typically there are really points, so it's going to be 0.00001. Well, if it is going to be higher than 0, then automatically you're going to be going to have a little bit higher chance to be in a higher category, yeah? And I'm sorry, if it is negative, in a lower category, yeah? If it is going to be positive, then automatically you're going to be in a higher category here, because we had a positive we had a positive beta here. And if it is so positive, it's over 1 in terms of like the z-scores. It's really loaded units, it's not z-scores. But it's highly positive, therefore there's going to be a high chance that you're going to be in a success category as opposed to the fail category. So it's really how you work with the success, the fail, the odds, the ln of odds, then you exponentiate the odds, and then the conversion back to the probabilities. And if you understand that process, then you pretty much understand everything in terms of logistic regression, and then the extension of the logistic regression to the multi-level problem. So some properties of loaded units, you can see that if I have a loaded unit of 2 and -2, they complement themselves with respect to the total probability. Yeah? So a loaded unit of 2, now, is the success rate going to be high here or low? What do you think? It's going to be very high because it's highly positive. Yeah. So this represents ln of odds. And the ln of odds is the loaded unit, and the loaded unit is very high. It's like z-score, yeah? It's very high. Therefore, the probability of success is very high, yeah? Now, what if it is 0? So the ln of odds is 0. What is the probability of success? 50-50, yeah? 50-50. So you see complement here, yeah? What if it is 0.5? Is it going to be high probability or low probability to be in a success? Yeah, it's going to be a little bit higher than 0.5. So it works out, the math works out that it's going to be 0.62. So if the beta is this, okay, and let's say your independent variable is also 0 and 1. So if you're in one category, you're going to be in a higher category as opposed to being in lower category. Yeah? So this is how the math works out. Actually, the way the formulas work is the EXP of the loaded unit divided by 1 plus EXP of the loaded unit will give you the probability of success. And the probability of fail is going to be 1 minus that expression. Okay, but we're going to look at the equations a little bit later. Now, this is if I plot probability, and here it's already probability which is confined to 0 and 1. And then I have my loaded units, which are, by the way, additive, linear, and multiplicative. Okay, probability is not linear, and we can see how it's not linear. And because it is not linear, when we have this type of situation, you don't want to use the ordinal least squares regression based on the general linear model. Yeah, because your regression will be estimating quite well what in the middle ranges, or for the students who are in the middle ability level, or patients that are not too severely distressed or too euphoric either, yeah? So, so if you think about it, okay, your regular regression won't really work in these types of situations because it will grossly underrepresent the extreme scores, okay, that are lying on the both spectrum of that, ability, okay? And then if you reverse it, and because before I had probability here and loaded units there, now I have loaded units that are stretching on the horizontal axis, and I have my probability that is on the vertical axis. And what do I get here? It's an S-curve, yeah? So that's, it clearly shows, as I progress on my ability level, you see a increase from 4 to 5, which is 1 standard deviation unit increase here, yeah, is associated with very little gain, yeah. But if I move here by 1 loaded unit, there is a huge gain in terms of the probability, yeah. So that's why it kind of goes with the, as a matter of fact, this is an S-curve, which is a logistic regression also, or logistic curve, we call it. But the cumulative normal actually has a very similar shape, okay? And that's why it's very difficult if you're kind of like the, brainiac in terms of mathematical achievement and you want to get a Fields medal, okay? It really takes even, maybe 3 standard deviations really to separate yourself from the best, okay? Because the movement here is going to be very, very small. So in other words, your ability might increase way to the right, but the relative gain is going to be maybe only 1% or something like that. It's kind of like, running 100-meter sprint. Okay, how do I be using Bolt? Well, I gotta be so much better here because I'm talking about the microseconds that are going to separate me from the winner, or him from me, or vice versa. But I can beat anybody who's kind of in the middle by moving just a little bit on my ability level. So if you think about the runners and their sprint time, 100-meter sprint times, being normally distributed, which they probably would be if you had a representative sample, then it would be similar type of distribution, okay, which is also a cumulative normal, but it's also a logistic curve here. Now, this is in terms of probability and odds, probability and loads. We kind of saw that already. I just exaggerated. And then, of course, you can think about this is your Z distribution and proportion. As a matter of fact, if you took and you did ability tests, or even when you test your patients or maybe students with perception data or something like that, and if you plot their abilities here on the Z-score in whatever way that you're measuring, their ability or their perceptions or maybe their attitudes or something like that, and then you plot the perception of correct or the perception of endorsement or something like that, let's say it was a binary outcome, you would also get this empirical S-curve. Okay, if you had enough people and if you had enough of discrimination in terms of the types of items that you're asking, it would be an S-curve. And then some examples of, this is of course your odds. So this is getting something right versus not getting it right, failing it. And then we know that it's not really odds, but it's the ln of odds, So how do I get rid of the ln? Well, I have to exponentiate both sides. So in terms of the left side, the ln goes away, But with the right side, what do I have? I have the exp. The exp stays, and that's the exponential function. And as a matter of fact, if I plot these odds as a function of something, and by the way, which one is the predictor here? I didn't label it X, but what would be the predictor? Well, the predictor could be, is this, A. It doesn't have to be X. So that could be being male versus being a female. Or this could be maybe GRE score or something like that, okay? It could be binary, or it could be categorical, or it could be continuous variable, okay? And this is what you're predicting your Y, except that Y happens in both places because it's Y and 1 minus 1. This represents success, this represents fail. And then you plot it, and you're going to get your logistic curve. Okay? Now, what do you think will happen if I decrease that coefficient? Okay, the line will become flatter. And then when I increase that coefficient, what's going to happen? What do you think will happen with the slope of the line? Okay, it will really, become steeper and steeper. Okay, so as I increase my beta here, okay, the slope of the line is becoming steeper and steeper. In other words, it takes less of a movement on the x-axis in terms of the independent variable that you're using to predict your outcome, because this is the plotted outcome. It takes less of a movement here and quite a drastic movement in terms of the y outcome. As a matter of fact, this type of relation, slope of the line, in measurement we call discrimination. So we would say this particular item is going to get discriminating better. Why does it discriminate better? Because a little bit movement on ability level will change quite significantly how your outcome is changing. Okay, so we're going to say, okay, this item discriminates between participants of varying ability levels in terms of the outcome there. And then this is what is going to happen if the coefficient is negative. As you increase here, the success, of course, is diminishing. So that's the negative coefficient here. But again, this coefficient represents also already a change in odds. Okay, if I took the exp out, this coefficient would be the log of the unit movement. Okay, but it's difficult to again be talking about the log of the unit movement, so it's easier to conceptualize that as just change in odds, which is the standard interpretation. And this is what we're going to be talking about this type of thing a little bit more in item analysis and when we move to rush models and item response theories. Now I said that the cumulative normal is going to be very similar to the logistic, okay? And this is, by the way, when we talk about the difficulty of items, we're estimating the difficulty of the items right in the middle of there at the point of indifference. Why? Is because the slope of the line, you will notice that the slope of the line is different at different points of the line, yeah? The slope here is almost, there is no slope, yeah? And almost there is no slope here. But the slope is going to be the highest here. Meaning the best precision that I'm going to get in terms of how the item differentiates between people is going to be in the middle of that line. And this is, as a matter of fact, where we think in mathematics in terms of derivatives. The derivative is simply a rate of change. The rate of change is going to be the highest here, okay? And that's the point of indifference, the 50-50, where z is 0. Okay, that's where most discrimination would happen. And that's where we estimate, what the ability is. Now, if we think about in space, and let's say we have two variables, and both of them are changing, then we're not talking about lines anymore, we're talking about surfaces. So this is, let's say, some kind of a continuous variable. It could be mathematical ability, and this could be a spatial ability. And this is how your odds are changing, is simply a surface like that. We're not talking about lines anymore when we have two. And when we have three, then of course we have volumes. And it will be very difficult to be really looking at volumes, okay? So the best, because you have output variable too. So the best that you can do in terms of three-dimensional space is when you have two independent variables, and the output variable is your y, which is your vertical axis, okay? So the 2 is the most that you can visualize. When you have 3, you can't really visualize it anymore. You have to break it down into 2 3-dimensional projections. And it's like looking at that corner and trying to see the 4th dimension here. So this is in terms of A and B, but now that's the effect not on odds, but actually on the translated probability of it. Because you can go from odds to probability, like I showed you. And this is what is happening. It's not going to be this S curve, but it's going to be kind of a plane, and it curves actually here, and then it curves here. So as I increase my A, I increase my B, the probability is increasing. Actually, I did it in reverse, so the probability is highest here. But it wouldn't change the shape really if I put 1 here and 0 here. It just would change the color, so you would get more of a red here at the top, okay? But this is pretty much, I increase my math ability, and maybe I increase my spatial ability, and the probability of passing a math item is increasing, but doesn't increase linearly, yeah? Because if it was a linear relationship, then it would be just a plane. It wouldn't curve at all, yeah? So it's kind of the same idea. It takes more of a change here and more of a change here to impact the probability at the bottom, yeah? So it takes way more ability to move the needle when you're already very good, okay? And likewise, when you're really, really bad, you're going to be way more worse, okay? And it's not going to change the outcome that much either, okay? So if you fail, fail hard. You know? I mean, it won't matter. Well, this is just kind of, we're playing around. This is what the cumulative normal distribution looks like in space. And by the way, this is the equation for the cumulative normal. I don't know if you want to mess with that, but that's what it is. As a matter of fact, these types of problems mathematically are very difficult to integrate, actually are impossible to integrate, because what you see here, it's the e to the power of negative power of something. And the negative power of something makes it impossible to integrate. So what you have to do in terms of the probability, how likely you are, with continuous variables, what you have to do is use numerical approximation techniques. And that's something that you do in numerical analysis in mathematics, as a matter of fact, is trying to figure out what the probability is if it is a continuous. Because with categorical outcome, I can do it easily. But with a continuous outcome, it becomes, it's like that C table, and you're wondering where the hell did it come from? Yeah, and you have your areas, if it is -1, then it's, between 0 to this, and between this to tail is this much. The very first question, where does the table come from? Yeah. How do we know it's 34% or 34.5, whatever it is, yeah, for non-standard deviation? Well, it comes from mathematical numerical approximation techniques. That's where the table is coming from, because you have to integrate area, but that area is not a rectangle or a triangle or anything like that. It's actually a smooth function. Yeah? Except you cannot integrate that smooth function, so you have to use some kind of an approximation technique to actually approximate what that area is. Now, in terms of the formulas, so the probability of success is this, which is EXP, and whatever the linear form. So here I have number of predictors. Yeah, I could have math ability, spatial ability, and maybe my intelligence or something like that, or whatever, and you're trying to predict how well you will do on a test. And it's the EXP of that, 1 plus EXP of that will give you the probability of success. And the probability of fail is going to be 1 over 1 plus EXP of that. And that's why when we're saying, when you take EXP of this, and this is already a logit unit, okay, because this is a linear composite, but the linear composite is basically compressed to a logit unit. So this is when we're saying it's 1 divided by 1 plus odds will give you the probability of fail, yeah? Because if I take a ln of that, then this EXP will go away, and I'm going to be left with basically odds. Or this is a logit, and I take the EXP of that logit, that gives me already odds. And then when I have odds divided by 1 plus odds, will give me the probability of success. Or 1 minus that will also give you the probability of success. So basically, you're working with these equations. And we start with something like that. It's a log of success to fail. So it's a log of odds. So this is a logit, yeah? And it's equal to that. And this is just simply a simple regression, yeah, to the right. Except I have the inconvenience of having the log here, so I have to do something about it. So I have to exponentiate. So now the log goes away, okay? But then I have the EXP here on the right side, so it becomes exponential function. So that's how you transition from the linear into the exponential. And of course, when you represent it like that, it's really like this, where the intercept values and the betas associated with the independent variables are really the powers of that base of the logarithm, okay, which is that e. And then, of course, when you multiply the e's, you can do it as e plus all of these terms, because multiplying logarithms is like adding them, okay? So that's, you know, how the math works. But basically, you're working with these two equations in terms of predicting what the probability of success and fail is. So in other words, you're basically thinking about classification procedure. You know, how likely you are you're going to pass the item or fail the item. How likely you are that you're going to agree with the item or don't agree. How likely you are that you're going to enroll in graduate program or not enroll. And we have some kind of a predictors here. Maybe this is family income, family structure, and the type of environment that you are grown up, okay? And maybe you're using all of these to predict whether or not you're gonna pass graduate school, or maybe you're gonna pass high school or something. Yeah? But instead of looking at how well you're gonna pass it, so you're not looking at GPAs, you're just looking at the outcome. Oh, you're gonna graduate, you're not gonna graduate. You're gonna be retained, you're not gonna be retained in the grade. You're gonna go to graduate school, you're not gonna, you know, the outcome is always binary on the left side. And you're looking with this type of probability statement, but basically what you're looking is working with the powers of these bases of natural logarithms. And I actually went through the trouble and I did the derivation of these formulas, because I never see them in a book. They just repeat themselves, and they just, you know, give you the final formula. But I was like, where the hell is the formula coming from? So I actually went through the whole thing, and you end up, you know, with these final equations. And we don't have to. It's actually a very simple algebraic manipulation. There's no calculus or anything, you know, involved in there. It's really very simple substitutions and a couple of tricks to basically arrive at that particular, you know, final equation. You know, so we have this is the success, again, EXP of that, 1 plus EXP of that, and this is the failure rate. You know, which is really 1 minus that, you know, as well. So this is a very simple derivation of this final We'll skip this one. And we'll look at a very simple example. And it's coming from our library card, which was designed by, or put together by James Fox out of McMaster University, Dr. Fox at McMaster University in Canada. Okay, and then he's looking at women participation in the workforce in Canada in various provinces, Ontario and Atlantic and Quebec and so forth and so on. And basically they were looking at number, and that was a study done in the 70s and 80s. They're looking at the factors that will make or basically predict women's employment. Okay, so they were looking at the family size and how high the income of the husband is, or whether they even have, and how many kids they have, and all of these types of things. And then they had a classification: work part-time, doesn't work, or work full-time. Now, of course, that would be a multi-level problem, yeah, because we have 3 levels: doesn't work, works part-time, works full-time. How many transitions do we have? 2, yeah. But now, to make it simple, I'm just selecting the not work and work, which is really the binary outcome that we want in the logistic regression. So the very first thing that we'll do is a classification table. And this is a classification table that can be easily done in R. Basically, you're looking at the independent variable absent or present kids. Okay, so it's not the number of kids. We're just making it dichotomous in terms of the independent variable too. You either have kids or you don't have kids, and then you either work or don't work. I know that there's more possible outcomes, but we're trying to make it simple now. And think about this logistic regression as a classification procedure. So from the distribution of these outcomes, where am I more likely to work full-time, if I have kids or if I don't have kids? Yeah, if I don't have kids, okay, I'm more likely to work. And I'm more likely not to work if I have kids. Now, again, we're talking about this study, from the 70s, 80s. I'm not sure whether it's true, anymore. And but that's basically, the distribution of these things. And if you look at it as a chi-square table, it will give you a chi-square statistic, and that chi-square statistic is going to be significant, meaning that there is something unique about having kids and the likelihood of whether or not you're going to work, okay, full-time as opposed to not work. In other words, you can use this to predict that, or even you can change the outcome variable to be the kids. Now, working would not determine really kids. Well, it could, yeah. If I work, maybe I'm less likely to have kids. Yeah, it's not really the kids that drive employment. Maybe it's the employment that drives the number of kids. It could go both ways. But in this particular situation, we're looking at kids as the independent variable, and we're looking at the employment side as the independent variable. But if you rearrange it, it doesn't have any impact whatsoever on any estimation and the coefficient and so on. And as a matter of fact, we're saying there is a relationship, and it's highly significant. Yeah? Because chi-square of 59 at degrees of freedom 1, it's 2 minus 1 times 2 minus 1, so it's 1 times 1 degrees of freedom is 1, yeah, for that chi-square problem. And then again, you can run it as a cross-tab, and you will get your Pearson chi-square, the same chi-square. And the one that is used actually in logistic regression is that likelihood ratio, and which is a little bit different than the Pearson chi-square, but very similar. And I don't want to go into the technical, explanation, why they're different, but it's highly significant. In other words, I can use the independent variable, whether or not you have kids, to predict whether or not you're going to be employed. And that prediction is going to be highly significant. So I have a dichotomous independent variable, and I have dichotomous dependent variable. And we were saying that that contingency table is highly significant. So I can use one to predict the outcome. Now, how would you do it? That's basically what you do in terms of the chi-square. That's the actual expected observed minus expected square divided by expected. It will give you the counts, and then you add all of these counts together, will give you the chi-square of 59. And that's really statistics 101 here, yeah, in terms of the chi-square and how you compute it. So now let's go to the actual example. How would you run it in SPSS. Now, I like to do it through a generalized linear model. So I go to that option, analysis, generalized linear model, as opposed to going through the logistic regression, because I have a little bit more of a manipulation that I can do here. But what you're selecting in terms of type of a model, you're doing a binary logistic model. Okay? Now, the next tab is what is going to be the reference category in terms of the response, and it doesn't really matter where you make it first or the highest, you know, but it makes easier to make the first one or the lower one as the reference category and then climb up as opposed to be stepping down. Yeah. So I kind of like to think about the reference category in terms of the predictor, in terms of dB, as increasing. Okay, with the baseline category kind of being at the bottom. And then the estimation model that I like to use is the Newton-Raphson, and I think that I mentioned before. If we go to the next slide, it's really an old idea from 17th century that was invented by Isaac Newton and then perfected by Raphson 20 years later. But basically what you're doing is you have that function, yeah, and you're climbing up the function, okay? And as long as the function is increasing, okay, the climbing up doesn't make sense. Because basically what that equation is doing, I have some kind of a theta is here, and I'm adding 1 to that theta. In other words, I'm moving a little bit more. Okay, and does the moving more, does it make sense? So first, when you get here, you reach the maximum of that function, and that already means you cannot improve anymore. As a matter of fact, if you move by 1, you're going to be dropping off. Okay, so the maximum likelihood for your performance is going to be at this level. And this is just a ratio of derivatives. This is first derivative, second derivative. As a matter of fact, if the first derivative reaches 0, meaning first derivative is 0 here because there is no change in the function, okay, whatever the second derivative is also going to be 0, so it's going to be 0 and 0. There is no improvement as you're increasing and moving up on that line, okay? Meaning I have found my maximum likelihood, you know, or the best coefficient basically that solves the equation. Now, in terms of the factors, doesn't really matter whether you put in descending or ascending, you know, way. Here it's saying that I'm going to start with having kids and move down to not having kids in terms of it. So we looked at how you're going to organize your dependent variables. Now you're saying, well, how I'm going to be looking at the factor or the independent variable. Yeah? And then I like to save the predictive categories and actually that linear composite as well, because the linear composite basically solves which category you're going to be in. And that's, you know, the solution basically, okay? You look at children. Now, again, children was what? Either having children or not having children. It was a binary independent variable, okay? And that negative 0.24 is the logit penalty associated with workforce participation. So in other words, it's in logit units or in z-scores. If you think about them as z-scores, if you can think in terms of logit units, this is how much more unlikely you're going to be to work. Okay, it's your penalty on working. So kids present, that's the penalty. Okay. Now, if I take the exp of that, because that's ln of odds, I'm going to be left with the odds. And these are the odds. And the odds are very low for you to work if you have kids. Okay? As a matter of fact, they are not even 10%. Okay? Because that's basically the ln of that. I'm sorry, the exp of that. Okay? Because that's already ln. Okay? So how do I get rid of ln? I have to exponentiate beta. Yeah? And that's what the logistic regression is doing. You have the beta, and you exponentiate to get to the odds, because it's difficult to think in terms of logit. Now, if you can think in terms of z-scores, you can think about it, okay, that's the amount of penalty. But if you want to think in terms of odds, let me exponentiate that logarithm and get to the odds. Okay? And the same kind of thing here, intercept and the logit penalty for having kids. And we're going to talk about what the intercept really means, because the intercept has a meaning also. Okay, and it's important to have the intercept and interpret it properly. Now, when we think about, again, the setup, so these were the actual counts, yeah, that we had. Have kids, don't have kids, and how many people are gonna, or women are gonna work versus not work, as a function of having kids. Now, when it doesn't really matter if you work with the column information or the row information. If you look at the total, 72, 46 divided by 72 is 0.64. Okay, 26 divided by 72 is 0.36. Therefore, the odds if kids are absent of working is 1.77. Okay, now let's look if kids are present. Basically, go through the same math. It's 0.13, 0.87. One divided by the other is 0.16. Now, the ratio of these odds, in other words, this divided by that will give you the 0.088. So that's how you solve it based on that chi-square or that classification. And you don't even need that logistic regression to tell you what the coefficient is, because, again, if you have categorical independent variables, that's basically what it is. Okay, these are the odds of working if you don't have kids. These are the odds of working if you do have kids. Now, where are the odds higher? If you don't, yeah? And then if you take the do versus don't, yeah, because we're using the don't as a reference category, so I have to look at the do, yeah, as opposed to don't. So I look at the do divided by the don't, then I'm going to get that 0.088. If you go to the previous slides, see, that's the 0.088, which is ratio of odds. Okay, and if you look at the other situation, this is the odds of having kids when working, and this is the odds of having kids if you don't work, which is a little bit, strange way of talking about the same thing. So we're talking about odds of having kids when working, not working, as opposed to odds of working when you have or don't have kids. Yeah? So you can reverse the whole thing. But anyhow, this divided by that will also give you the ratio of odds, which is that exponentiated coefficient, okay? Because the penalty in terms of log of units was negative 2.4. If you exponentiate that, then you're actually going to get to that specific, to that ratio of odds, which is what that coefficient is. Now, why do we need the baseline, the intercept? And I guess that's going to be the last concept that I'm going to introduce, and then we're going to continue with the same topic. But basically, you need the intercept to determine what the baseline probability is. Okay, so if my reference category is having kids, my baseline is going to be not having kids. And then if you plug it into that probability function, exp of that intercept divided by 1 plus exp of that intercept, you're going to get the probability of the baseline category, because you can know the ratio of odds and the odds, but you still don't know what the probabilities in that reference categories are. And as a matter of fact, if you use that intercept, it will give you that baseline probability. And that's what maybe one more. Yeah, that's what is happening here. Penalty for having kids. Okay, this is if you don't have kids, basically, yeah. Because if you have kids, you use this plus that. If you don't have kids, then you use just this, because if you don't have kids, the x is equal to 0, so 0 times this, it goes away. So if I just take the intercept and plug it here, I'm going to get the baseline probability, likelihood of working in terms of probability, if you have or don't have kids. Now this probability is what? I'm just using the intercept, and I said that to get to kids, I have to subtract that, but I'm not subtracting anything, therefore I'm computing probability of what? No kids. Yeah, because if I do have kids, then I have to do this plus that, which is basically here, this plus that. So that's going to be your penalty. As this number goes down, the probability will be going down. Okay? because anything that is negative, if you exponentiate a negative number, is going to be a very low probability. Okay? If I was adding here, if it was a plus, if it was plus 2.45 or 4.35, then that would be adding to the probability of working if you have kids. But that would be going the wrong direction, because if you have kids, you're less likely to work. Well, maybe nowadays you have to work more because having more kids is more demands and you know, more bills and more demanding situations. So it might be actually a little bit different in today's reality. But that's basically what you need. That you have to compute the baseline probability. And again, once you have your baseline, anything that you add in terms of the reference is how much benefit or penalty you have to being successful. And what is the success? The success is whether or not you're going to work, or whether you're going to work is the success, because we chose the reference to be working as opposed to no work. So that's kind of, you know, what is neat is actually you can compute all of these numbers just for that 2x2 table. You can get your chi-square, which is the wall statistic and logistic regression. And you can even compute the ratio of odds, because once you have odds for people who work and odds for people who don't work, then you can compare these as a ratio, and that's what that EXP of that loaded unit really is. And that's what is being estimated in logistic regression. But ultimately, what you want to interpret is the odds. Okay, and from the odds, you can compute what the specific probability, how likely you are to work versus not work, depending on whether or not you have kids. That's kind of the same idea, but it's, you know, a little bit more complicated because you have to go through that odds and really a ln of odds, you know, kind of translation, because we're not dealing, we have linear something on the right side. Well, it doesn't have to be linear, it could be also categorical, but the right side is linear. The left side, nothing linear, it's just a binary response, yes or no, agreed, disagreed, was present, was absent, I failed, I passed, I'm going to enroll in the program, I'm not going to enroll in the program, I'm going to come to the next workshop, I'm not going to, you know. The instructor is boring, the instructor is, you know, these types of things. So you need a translation mechanism, and the translation mechanism between the linear on the right side and the nonlinear on the left side is that logistic function, because you have to get rid of the ln of odds. And the only way to get rid of it, you have to exponentiate. So that's why we go through the exponential function. And we're going to continue with these types of ideas. And again, if you want to kind of refresh and look at it again, you know, we have the presentation available. And then we're going to be talking about multi-level applications as well, which are very applicable because most of the situations we're dealing with categorical outcomes. Very rarely we have scale scores like GREs or SATs. I mean, any research that we're doing is really which category you belong to. Yeah. So that's why it makes sense to use these types of methods as opposed to just simple linear regression. All right. Well, thank you for coming and supporting the workshop.